Hello everyone, welcome to this virtual presentation of the paper Quick Opportunities and Threats in SATCOM Systems, a virtual presentation for the conference ASMS SPSC 2020. My name is Nicolas Kuhn, and this is a work done conjointly with my colleagues, which names can be found on this slide. Why do we focus on Quick? Quick is actually being standardized at IETF and is already deployed by several companies such as Google Services, Facebook, but also some web hosting companies, Akamai, Cloudflare or Fastly. And it is worth noticing that in 2019, Quick was accounting for around 25% of the traffic share. So this has been found by Joan Roots in a paper entitled How Much of the Internet is Using Quick. What is Quick? As opposed to a classical stack HTTP2 over TLS over TCP over IP, Quick is in between HTTP3 and UDP. So Quick includes most of the functionalities that are provided by TCP, such as reliability, flow and congestion control, multiplexing, and so on. But on top of TCP, we have the guarantee of confidentiality, integrity, authenticity of the data and transport parameters that are in a Quick transport. Let's have a look at how a Quick packet is formed. If we have a stream of index S, the offset O is where we are in this stream at the moment, and we have a flow control limit. So this gives us the data of the L that we would like to send in a stream frame. There are many types of frames within Quick, such as crypto, acknowledgements, or any flow control information. And a Quick packet is composed of a bunch of data that could be the stream frame and two acknowledgements, crypto, and so on, and a long header. Can also be a short header, but in this presentation we only show a long header. So in this presentation, we will start by looking at what are the challenges for Quick in SATCOM systems. We have used a laptop connected to a KSAT SkyLogic offer, which is a public satellite-based internet access, and we download two targets that are located in Google servers, so target A and target B. Target A is a large object, target B is composed of three small objects. What we can see if we start by looking at target A first is that with Quick it takes up to 9 seconds to download the file, as opposed to less than 5 seconds with classical TCP and acceleration mechanisms. When we look at target B, because Quick includes quick handshakes, we have a way lower page loading time. So we have a problem here with large files. Another challenge that Quick will encounter when we use it over SATCOM access is that we will have end-to-end losses. To measure these end-to-end losses, we have downloaded using the same public internet access different files from a PicoQuick server located at either. What we can see here using an end-to-end internet access is that when we use a wired access, if you look at the second column of the table 1, we can see that we have more than 1% end-to-end losses. So we have proposed a Gilbert-Elliott model to see reflect the bursts of losses, but I will not go into the details here. What matters for us is that these losses may have a very large impact on the end-to-end flow. Here we have an end user connected to an HTTP server. This is done in our lab using a real satellite. And what we can see is that when we lose, for example, the third line of the table here, that if we lose 5 packets over 1,000, the good boot is halved. So to put it in a nutshell, if we look at the strengths of Quick, Quick has a very quick handshake, and this results in that the first data, it is faster to transmit the first bits of useful data as opposed to classical solutions. However, the weakness that we have found is that the congestion control convergence can be long, and we cannot have local retransmissions, and this have a very huge impact on the output for the end-to-end application. That being said, with Quick, ground segments are cheaper, and SATCOM systems might be more integrated, and we can adapt tune Quick to our use case because it is a very flexible protocol. And the threats we have identified is that we may not be sure to control how the protocol will evolve, and this may have impact on QoE in the long term. So we have proposed at the IETF a framework. The main objective is to have agree as a community on what are the objectives for Quick in a SATCOM system. So we have these tests that are listed in the draft, and we have proposed some examples of what we would like to obtain in terms of performance. So in this paper, we propose a framework that can be exploited by anyone to contribute to the definition of the outcome of the regression tests. And also, we aimed at providing the open source code for replaying all the scenarios. That this is ongoing work. We haven't done it yet, but we have exploited only open source tools. And so if you want to set up what we have set up, do not hesitate to contact us, and we would be happy to help. So because we want to contribute as anyone to the definition of the objectives for Quick, we do not pretend to generalize all our results, because it depends on the kernel versions, what options we have in proxies, and so on. But we would like to come up with performance objectives that are challenging enough and good enough so that satellite operators allow Quick and not block it. But also these objectives must be reasonable enough so that they can be actually deployed on the internet. So the test bed we have used for the results I will show later on is described in the figure on the left here. We have one iPerf server and one iPerf client end-to-end, and we have two PEP cells on both sides of the satellite axis. The capacity between the two PEP cells depends on the scenario, and we have considered different PEP configurations. So basically the main difference is the initial connection window and the size of the buffers for the TCP sockets. So our objective is to obtain and configure and tune the PEPs to have the best performance ever, but it's to contribute to reasonable objectives. I'm sorry for the figures here, the values are not accurate. We have a 50 megabits download and 10 megabits upload access. And when we can see, if we look at the picture at the top, excuse me, is that if we look at the purple, green, and yellow and a blue curve, adding a PEP doesn't change much things. And both are not able. Both in these cases, the flow is not able to reach the available capacity. When we look at the PEPs where the initial the buffer sizes are increased, that are orange and yellow, we can see that they can reach the available 50 megabits. Based on that, we propose values objectives for Quick that are listed in the slide here. We have also looked at a more challenging case where we have 250 megabits upload and download and 3 megabits upload, but also random losses after the satellite terminal. In this case, we can see that, as opposed to the previous slide, purple, when there is no PEP, the purple line does not do as good as the green and the blue ones. We can see that because of the loss, 1% loss, the PEP, the end-to-end flow cannot use the capacity at all, and we have the same limitations for PEP A and PEP B, which is that they cannot grab more than 40 megabits per second. And so this illustrates that local recovery of packets helps, and actually reduce the transmission time. But in this case, we also have the fact that we need to increase the buffer sizes to actually reach the available capacity of the network. We have shown in here some cases where it is very complicated for Quick to have good performances in SATCOM access. Here we discuss some of the ways we could improve it. One thing that could be done could be to adapt the condition control and be more aggressive than what we have on the default Linux stacks. Another thing that can be done, and we have a draft at the IETF for that, is to actually exploit the information from previous connections to help when we resume a connection to actually fastly fetch the available capacity. To overcome cope with losses, we could do local recovery of losses or introduce coding. Another way to improve things would be also to introduce quick proxies, but they have security implications that we do not want to address. As a summary, Quick may replace the historic and ossified TCP, and we think it's a very interesting opportunity for SATCOM systems because it reduces the amount of handshakes and it actually improves the transmission for short flies. That being said, we don't have local recovery, and that may induce a very important output reduction. So Quick does not outperform TCP proxy solutions, but still achieves very good performance, and we think there is much to be done, work to be done to actually do it even better. So we propose running code for in an IETF document, which we hope to release very soon. This is all based on an emulated platform and open source software, and we propose values as an example as one piece of the puzzle. We encourage the community to reduce our framework, to propose quick extensions, to challenge and do something that is as good as what we can have with TCP proxy. And we just have to keep in mind that these objectives must be challenging enough for satellite operators to not block quick traffic, but also reasonable enough to be deployable on the internet. I hope that this presentation made you want to actually read our paper, and please, if you have any questions or remark, please send us an email. We will be happy to answer and interact with you. Thank you very much.